Welcome to the Combined Physics Paper 1 revision PowerPoint on particles, particle model, the first topic, Combined Paper 1. You're going to be asked to use the idea of particles, their behavior, their arrangement, their movement, the forces between them, to explain the properties of solids, liquids, and gases. First thing you're going to be asked for a 4 or 6 mark question is to describe how the particles in solids, liquids, and gases are arranged and how they are moving. When we want to describe how they are arranged, we describe the particles in a solid as having a regular arrangement, the particles in a liquid as being in a random arrangement, and the particles in a gas as having a random arrangement. The particles in a solid are closely packed with strong forces holding them together. The particles in a liquid are closely packed with weaker forces holding them together. The particles in a gas are very widely spaced with no forces holding the particles together. In terms of the movement of the particles in a solid just vibrate in a fixed spot, whereas the particles in a liquid are free to move and slide past each other in all directions. The particles in a gas are constantly moving in random directions and at random speeds. So you might be asked to use the ideas about the particles to explain the properties of solids, liquids, and gases. For example, you could explain the idea that solids always have a fixed shape, a definite shape, by explaining that the particles are really strongly bonded to each other, held together by strong forces, or the fact that liquids can flow by using the idea that, hey, the bonds between those particles are weaker, so they're free to slide and move past each other. Why can gases spread out or fill up a container completely? Because they're completely free to move. They have no bonds between the particles. When we look at how closely packed or how closely or strongly bonded the particles in solids, liquids, or gases are, we start thinking about this idea of density. The more particles there are packed together in a certain volume, the greater the density of the material. If you took the same volume of a different material with the particles packed more tightly, there would be more particles in that volume, so it would have a higher density. To calculate the density of a material, we use the My Dog Vomit mass density volume formula. Mass has to be recorded in kilograms. Density is measured in kilograms per meter cubed because we always measure the volume of materials in meters cubed. So mass, density, volume, My Vomit. This is a required practical to be able to work out the density of a material, and it comes in 2 varieties. A required practical where you might be asked to work out the density of a regular object like a cube or a cuboid. So to work out density, you need to measure the mass and you need to measure the volume. To measure the mass of a regular object, place it on an electronic balance. To work out the volume of your regular object, measure the sides of the object using a ruler, and then calculate the volume using your length times width times height formula. Now you can work out the density with density equals mass divided by volume. If it's an irregular object, a strangely shaped stone or something you can't measure the volume of with a ruler, then we're going to do the practical slightly differently. We'll still measure the mass of the object on the electronic balance. So put it on the balance and write down its mass in kilograms. But we're going to use our Eureka beaker or Eureka can to measure its volume. Lower the object into the Eureka can and measure the volume of water that comes out using your measuring cylinder. Now you've got the mass and the volume of the object, you can calculate density equals mass divided by volume. Now when we look at the energy that's contained in the particles in solids, liquids, and gases, we call that the internal energy, but it's made of 2 parts. Of course, the particles have energy because they're moving, they have kinetic energy. The particles in a solid just vibrate, they don't have very much kinetic energy. The particles in a liquid are moving at all times in random directions, and the particles in a gas are moving at very high speed in random directions. So they have different amounts of kinetic energy. But we must also think of potential energy. Potential energy is the energy in the bonds between the particles, holding the particles together. So the internal energy is the total of the kinetic energy and the potential energy in that system, in that solid, liquid, or gas. If we add potential energy, What we're doing is we're helping to warm something up and then change its state. So if you warm up a solid, it will melt and become a liquid, then it will get warmer and warmer, and eventually it'll evaporate and become a gas. If we lose internal energy, then the temperature goes down and the gas will condense and become a liquid, and then the liquid will freeze and become a solid. There is one change straight from a solid to a gas called subliming. That requires you to add internal energy as well. Now that means that when we heat up an object, the energy we're putting in is sometimes going to raising the temperature of an object and sometimes going to changing its state. So when we heat it up, then we notice that the temperature doesn't go up steadily. As I heat something up, to start off with, the temperature goes up as that energy changes the temperature and warms up that solid. But when it reaches its melting point, then what's going to happen is that the energy we put in is going to be used to change the state of the material. So adding internal energy now isn't increasing the temperature, it's changing the state. Once all the solid is melted and become a liquid, now the energy you put in is going to change the temperature again. The liquid is going to get hotter and hotter and hotter until it reaches its boiling point. And now the energy I add is going to start changing the liquid to a gas, changing its state. Once all the gas is turned into a liquid, then the energy you put in will just increase the temperature of the gas. So as we add internal energy, that extra energy either increases the temperature of the material or changes its state. You cannot do both at once. To work out how much energy we need to heat up materials, we use a number called the specific heat capacity. And that's the amount of energy needed to change the temperature of 1 kilogram of a material by 1 degree centigrade. For example, copper has a specific heat capacity of 387 joules per kilogram degree centigrade. Aluminium has a specific heat capacity of 900. That means it takes more energy to change the temperature of aluminium than copper. So this is the energy that's being used in the changing temperature parts of the graph. The energy being used to warm up the solid, or to warm up the liquid, or to warm up the gas. And we can calculate how much energy it takes to heat up the solid the gas by using the specific heat capacity equation. This is given on the formula sheet. You don't need to learn it. The energy we need to change the temperature is equal to the mass of the material in kilograms multiplied by the specific heat capacity multiplied by the change in temperature. So how many degrees it has gone up or down. Now there's a required practical you need to know to work out the specific heat capacity of a material. And the way we do that is we take a block of that material and wrap it in some insulation, and we're going to heat it up using an electric heater. Once the electric heater is plugged in, we're going to need to measure 3 things. First, we're going to measure the mass of the block on electronic balance. So you write down its mass in kilograms. Then, once we've heated it up, we can measure the temperature change, how many degrees the temperature went up, using our thermometer. Finally, we can measure how much energy went into the block by using the joule meter that's connected to the heater. Now we know the mass, the temperature change, and the energy transferred. We can use our specific heat capacity equation to work out C, our specific heat capacity. The changing state part of the graph, we use a number called the specific latent heat. And that's the amount of energy needed to change 1 kilogram of a material, either from a solid to a liquid or from a liquid to a gas. It's the changing state number. There are 2 different sorts. The specific latent heat of fusion is the energy needed to change 1 kilogram of solid to a liquid. The specific latent heat of vaporization is the energy needed to change 1 kilogram of liquid to a gas. That's the energy in this calculation. Again, it's given on the formula sheet, no need to memorize it. The energy you need to change something's state is equal to its mass in kilograms times that specific latent heat number. That's the energy that's being used in the changing state part of our graph.